Pleasure to introduce Eknath Ghate, School of Mathematics, TIFR. Professor Ghate works in p-adic representations and L functions. He received the Shanti Swarup Bhatnagar Prize in 2013. Today he's going to talk about mod P representations. Eki, please begin.
Thank you very much. So thank you, Professor Prasad, for that nice introduction, and thank you to the three organizers who put in so much effort. Just told me that you're doing this 12 hours a day for 5 days, so that's rather incredible. And it's also a good opportunity for older people like me to learn some technology and get to use these virtual platforms to give talks and things. So I will speak about mod P representations. That's the title right there. And that is the Bruhatitz tree, in case you're wondering, that picture. I'll come back to it in the talk. But that is the central picture for the talk, actually. You know, they say all of mathematics is linear algebra or graph theory, but so here's a bit of graph theory. Okay, so here's the overview of the talk. So let P be a prime number. And I'm going to work a lot with these p-adic integers. So ZP is going to be all, as algebraically, you can just think of it as numbers and with some base P expansions, but they have infinite tails. So R0 plus R1P plus R2P squared, where Ri is 0, 1, 2, 3, up to P minus 1, okay? So, you know, we are familiar with decimal expansions, and we usually terminate these things. But if you keep going here, then, and P is a prime, then you get the p-adic integers. So that's how you can think of these algebraically. You can add these things by doing some carries and multiplying also by doing something similar. So QP is the quotient field of ZP, of ZP, and it's the field of p-adic numbers. So again, this is all quite algebraic, but you can also think of QP as the completion of Q with respect to the p-adic metric. So, you know, you can have this dictator who decrees that two numbers are close if they're highly divisible by 5. So for example, 25 is quite close to 0, but 125 is even closer to 0, and so on and so forth. 625 is very close to 0. So this gives some sort of metric on Q, and if you complete Q with respect to this metric, you get also QP. Okay, so we have the p-adic integers and their quotient field, the p-adic numbers. And finally, you can also go mod P. So starting from ZP again, from ZP again, you can go mod P, and if you go mod P, you kill all the terms R1P, R2P squared, etc., and you're just left with R0. So that's P by this 0 to P minus 1, that's P elements, and in fact, you get the field FP, finite field with P elements, which everybody knows. So in this talk, we'll be interested in certain representations of two groups in particular. So I'll denote by G the 2 by 2 matrices with entries in QP, invertible matrices, and I'll denote by gamma the 2 by 2 matrices with entries in FP, the finite field with P elements. Okay, so these two groups will play a very important role in this talk. And I will be interested on the actions of these groups on vector spaces, often infinite dimensional, usually infinite dimensional vector spaces, over a field of characteristic P, but more precisely over FP bar, the algebraic closure of FP. And we will just call loosely any such representation as a mod P representation, either of G or of gamma. Okay, we should also be interested in connections of these mod P representations of G or gamma with Galois representations, and in particular with mod P Galois representations. So I'll define those much later towards the end of the talk, and using what are called Langlands correspondences. Okay, that sounds a bit fancy now, but we will see that everything is very concrete. Okay, so that is the overview of the talk. Basically, we'll study mod P representations of G, and we will see how they're connected to mod P representations of the Galois group of QP, which will come up later. Okay, so let's start with some representations of gamma. So let VR be the space of all homogeneous polynomials P in two variables, x, y, of degree R greater than 0, with coefficients in FP bar. So these are just your usual polynomials in two variables, coefficients are in FP bar. And they're homogeneous. So the degree is 10, it'll be like x10 and x9y and x8y squared. That'll be a basis as a vector space. So the finite dimensional thing, dimension R plus 1 if you have degree R. So this has a natural action of GL2FP on the space of polynomials. You just substitute for the variables. If you have a matrix A, B, C, D in GL2 of finite field, you just take x to x plus cy and y to bx plus cy, and you get a natural action of the group on this vector space. So this is a model for the symmetric arc power representation of the standard representation for the experts. But you can just think of this very classically as just 2 by 2 matrices acting on polynomials, sort of a high school kind of object. Now it turns out that unlike the complex numbers where these representations are irreducible for all R, these particular VRs, if you have GL2 FP acting on this mod P vector space, it's not always irreducible. In fact, it's only irreducible for small values of R. And then when you cross R equals P and onwards, it becomes reducible. And in fact, if you want to write down all irreducible representations, you can just use these. VR basically are the models of all of them, as long as you're willing to also twist by powers of the determinant. So GL2FP, if you take the determinant to get something in FP star, and if you take it Sth power, then these are just characters, and you can twist this representation by d to the s. So these are all irreducible mod P representation. That's a complete list. Okay, so the question immediately arises, what is VR for larger R? And it has many interesting subquotients, and it has many interesting subrepresentations and quotients. And of course, the Jordan-Holder factors of these representations will, or these subrepresentations or subquotients, will always be from this list, this finite list. Okay, P times P minus 1 representations. So we will study a few of them here, and I will tell you why the particular ones we'll look at are important soon. So one class of sub-representations you can look at are the monomial submodules of VR. So this is again a very elementary thing to do. You just take, for example, x to the power of r, when I is 0, that xr minus I is generated by xr minus I y to the I, that particular monomial. You just take that particular monomial and look at the gamma submodule generated by that monomial. Okay. So I should say that before I go further, just, for example, if you have R is P and you look at x to the P, then how does a matrix act on x to the P? I would have written something here on my slide, but I'm a bit nervous to use my pen. So x to the P just goes to AX plus CY to the P, and by the freshman's dream, that's just A to the P, X to the P plus C to the P, Y to the P, right? That's the most stupid version of the binomial theorem in characteristic P. So X to the P is not generating something very large. It's just generating a two-dimensional space. A to the P, in fact, is just A. So it's just, all you get is X to the P and Y to the P. It's a very small submodule, two-dimensional. And this is happening because it's allowed to happen because these VRs are not irreducible, they're reducible. So you can get something small. Okay, so the question arises, what are these submodules? What are their structure? What is the lattice of all submodules inside VR? So I'm going to restrict to the first P submodules, XR, XR minus 1, XR minus 2. Somebody keeps writing on my slides. That's not me, by the way. It's one of the hosts, so please be careful. XR minus P minus 1. So it's not at all clear, but there are inclusions between these monomial submodules. For example, let's look at the first one, XR and XR minus 1. You want to show that XR is sitting in XR minus 1. Well, you need to write the monomial X upper R as a linear combination of vectors in X lower R minus 1. And that particular linear combination works because if you if you make 1101 act on xr minus 1y, then the x part hasn't changed. This acts by columns, so x just goes to x, but the y goes to x plus y. And so you'll get x to the r plus x to the r minus 1y, and then you cancel off the x r minus 1y. So you can see that xr is a linear combination of vectors in the second space, and so the first inclusion holds. And you can do similar tricks to show that, in fact, all those inclusion holds. It's a bit deceptive because after this, things begin to break down, which is why I've restricted to this particular list. Okay, so let me make a definition. For any I between 0 and r, you can look at the sum r minus I plus I, which is of course equal to r, but try and do this in base p, in those base, using the p-adic digits. And as in base 10, as we all learned in school, when we're adding numbers, then, you know, if you have 3 plus 7 in the units, you get a 10, so you get a 0, you have to carry a 1. And there's some carries. And because there are just two numbers here, you just get a sequence of zeros and ones when you try and do this addition in base p. So yeah, so there's a sequence of zeros and ones that we get, which is called the carry pattern of the equation above. Okay, so as soon as you have an I, you canonically get a sequence of zeros and ones, the carry pattern of that particular summation in base p. For example, if you want to do some, of course, if you write, if I is 0, then r is equal to r plus 0, and then the carry pattern is just 0, 0, 0, 0. There are no carries. But a bit more interesting, if you take r minus 1 plus 1, so if p does not divide r, then there'll be no carries when you add r minus 1 and 1, right? Because if p does not divide r, then the last term, the constant term in that base p expansion, is non-zero. So r minus 1 is, you don't have to do much. You just have to subtract 1 from the constant term. And then when you add it back, there's nothing going to happen. You won't get any carries. But if p divides r, it's a bit more subtle, because if p divides r, suddenly the base p expansion of r minus 1 changes, right? Because there's nothing to subtract from the constant term. You have an r1p and then an r0, but r0 is 0. So when you subtract 1, you're not allowed to put a minus 1 in the constant term, right? So you have to write a p minus 1 there by borrowing a 1p. And then when you add a 1 back to it, then you will get a carry. P minus 1 plus 1 becomes p, but you're not allowed to write p, so you'll get a carry of 1. Okay, so it's very elementary. Each time you get some sequence of zeros and ones, carry pattern. Okay, so here is a rather remarkable theorem, which unfortunately is not true in our setting, but is true if you replace GL2FP, which is a finite group of Lie type, by some sort of algebraic group, GL2FP bar. So it's GL2 with infinitely many entries in it. And the theorem says that there's an isomorphism of lattices between the monomial submodules of VR. So those are the things we're trying to study with respect to inclusion, and carry patterns with respect to lexicographic ordering. So this is a theorem of Doty from 1989. Okay, so lexicographic ordering is just the dictionary ordering. Right, 0, 0, 0 comes before 1, 1, 1, and so on and so forth. 0, 1 comes before 1, 1, etc. So this is really a remarkable theorem. It's telling you all possible inclusion relations completely in terms of the relations between the carry patterns. Okay, unfortunately, this is no longer true when we replace gamma bar, which is an infinite group, GL2FP bar, back with gamma, which is GL2FP. So here's a silly counterexample. We just did, when p does not divide r, we just looked at the carry patterns when I was 0 and I was 1. When I is 0, of course, the carry pattern is always a string of zeros. But when I is 1 and p does not divide r, then we still get this sequence of carry patterns, trivial sequence, 0, 0, 0, 0, 0. So that means that it looks like xr should be equal to xr minus 1 because they had the same carry pattern by Doty's theorem. But Doty's theorem doesn't work here. Turns out that xr is strictly contained in r xr minus 1 if r is greater than or equal to p. And that's not such a hard computation. I've given some references to things I say, which are on the last slide. So that's one of the references, Eknath Ghate, 2015. Okay, so can we rescue this in some way? And it looks pretty nasty, but here is a nice lemma. So we need a little bit of notation. So let sigma PR be the sum of the p-adic digits of R. So R0 plus R1 plus R2 plus 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 Rm. In base P expansion, R is an integer, so it stops. So you can add these things up. A regular integer, not a p-adic integer. And the lemma is this, that if R is greater than or equal to P and J is smaller than I, but always between 0 and P minus 1, remember that we know that XR minus J is sitting in XR minus I because we had those strings of inclusions. But they're in fact equal exactly when I and J have the same carry patterns, but in addition, you have two more conditions. The sum of the p-adic digits of R minus J has to be small, and the sum of the p-adic digits of R minus R naught was the constant term in the base P expansion, that also has to be small, less than or equal to J and less than or equal to P minus 1. Okay, so that, notice that the fact that I and J have the same carry patterns is a necessary condition, because if XR minus J is equal to XR minus I over FP, when you work with GL to FP, then it's necessarily true over GL to FP bar, right? They're the same generators. So it forces that I and J have the same carry patterns by Doty's theorem. But it's not sufficient. You need two extra conditions to guarantee equality there. Okay, so this is some kind of flavor of how things change when you move from GL to FP bar to GL to FP. Okay, now what about the actual structure of these modules? So let P be greater than or equal to 3. Eventually, P will be even 5 or more. The structure of XR, as I said, XR can be quite small. Remember when R was P, then XR was just a two-dimensional representation. It's just something quite small. But in general, XR has at most two journal holder factors. And XR minus 1 this was due to Glover in 1978, the previous result. XR minus 1 was studied much later. Surprisingly, these kind of high school things, there's not much literature on them. And we looked quite a lot and then had to do everything by hand. So XR minus 1, remember this is the gamma submodule, GL2FP submodule generated by XR minus 1Y. And this has between 2 and 4 journal holder factors. And these can be determined quite explicitly. Remember, I gave you a complete list of the P times P minus 1 journal holder, all the irreducible representations. You can really write down which ones occur in which cases. Basically, it's a 3-part theorem. I won't get into it now. But everything can be done very explicitly. So here's some joint work with Raviteja Vangala, who was also speaking, I think, giving a short talk at the end of this conference in more details about some of the things here. But here is one of the theorems. It says that if R is sufficiently large, then the structure, and if the sum of the p-adic digits of R minus R naught is sufficiently large, bigger than P, then XR minus I is very simple. It's just the tensor product of two fairly known representations. So XR minus I is the tensor product of what I call XR minus I comma R minus I. So this is the gamma submodule generated by X upper R minus I, but in VR minus I, lower I. Okay, so that's why the 2 commas, because it's a bit ambiguous, the notation. And then tensored with VI. VI is sitting in, is just VI. Okay, so it's a tensor product of two smaller things. And there are these representation theory, if you try and do any representations of SU2C and things, there's something called Clebsch-Gordon formulas. Very nice formulas that if you have two irreducible, then you tensor them, how they decompose. And so these kinds of formulas also hold here. So once you know that something's a tensor product, you can apply Clebsch-Gordon formulas to actually find the full structure of XR minus I. So this unfortunately has a condition that the sum of the p-adic digits of R minus R naught is a bit large. That's the generic case. It usually will be large. But if it's small, if the sum of the p-adic digits of R minus R naught is less than P, then the structure of XR minus I can also be determined in terms of explicit tensor products and certain irreducible principal series representations, which I will get to in a second. So I won't tell you exactly what it is, but I will tell you what principal series representations are. I should say that isomorphism looks a bit mysterious, but it is not at all mysterious, because on the right-hand side, you have the monomial X upper R minus I, which sits in VR minus I, and you have Y to the I in VI. And if you multiply those together, you get XR minus I YI. So there's a map from the right to the left, multiplication map. And it's that multiplication map which becomes an isomorphism. Okay, so what are these principal series representations? So some standard notation. We look at the upper triangular matrices in gamma. It's called the Borel subgroup, the standard Borel. A, B, 0, D, where the diagonal entries are non-zero elements in the finite field, and D is in FP. And we look at a character chi acting on such matrices. So we just look at the diagonal things and we take a b0 d to a to the m d to the n, where m and d are integers. Okay, so this defines the character chi of B. Should turn my phone off. Okay. So for such a character, we immediately get a p+1 dimensional representation. What you do is you look at all functions from gamma to fp. So these are all functions from GL to fp to fp. This is like a, almost like a computer science talk. So everything is finite here and finite dimensional so far. Right, we're working over finite fields. So these are functions, arbitrary functions, not homomorphisms or anything, from GL to fp, but it has one relation, and that is that f of h gamma is chi of h times f of gamma. So chi of h, remember, was something in fp star, so you're just multiplying by a scalar, and f of gamma was something in fp, so again another scalar, you're just taking the product of two scalars there. This is for all h in the Borel and all gamma and gamma. So if you have this condition here on the left, then you can make an action on the right. Gamma can just act on the right. It won't change your condition and it'll preserve this space. And so this is called the principal series representation of gamma. And because the index of B in G, the index of B in gamma in GL to FP is clearly p+1, right? GL to FP mod the upper triangular matrices, that cardinality of that thing is p+1. This representation has dimension p+1, and it cannot possibly be irreducible, because remember, irreducibles stop at p, dimension p, because p-1 was the last one. So that has dimension p. So this is almost irreducible. It's just beyond that range, and it has two Jordan-Holder factors. Okay, so these kinds of principal series representations can be used also to describe the structure of the monobial submodules, and they come up in many places. So I thought I'd recall the definition here. Okay, so that's one kind of submodules of VR, and there's another very interesting set of submodules of VR, which I will describe now. So these are the theta submodules. So what is theta? Theta is a very concrete polynomial, sometimes called the Dixon polynomial, x to the p y minus xy to the p. This has the remarkable property that GL2FP preserves this polynomial, in the sense that if you make a matrix act on that, then you'll just get the determinant pulling out and you'll get the same polynomial back, right? So it acts on theta by the determinant. That's a small computation, and this uses very, very heavily that you're working in GL2FP and not in GL2FP bar. So this is something completely new to GL2FP, because you want to use things like a to the p is equal to a and things like that for scalars. Okay, so for each of these, for theta, we get these submodules, and they're very easy to define. VR upper m. They're just all the polynomials which are divisible by theta m times. Okay, so VR1 means all polynomials which are once divisible by theta. VR2 means all polynomials twice divisible by theta, so on and so forth. Okay, so clearly there's a filtration. As you have more and more divisibilities by theta, you have this. And ultimately, of course, you'll go off to 0 because R is finite and the degrees of these things are increasing. So notice that there's some elementary facts about these VRMs. So first of all, the first one is very easy. The first one just says that VRM is basically another VR, but for a smaller r. R minus m p+1. The degree of theta is p+1, right? That polynomial at the top of the page has degree p+1. So what you're left over with something of that degree, r minus m times p+1. And because you've pulled out the theta, the action is by determinant to the m. So that's more or less obvious, the first thing. So individually, they're not that interesting. They're just shifts of VR up to twists. And the quotients are also fairly interesting. The quotients are actually principal series representations. So VRM mod VRM plus 1 is induction b to gamma, a to the m, d to the r minus m. So as on the previous slide, in particular, they're p+1 dimensional, which they have to be, right? Because you're dividing by theta. So each one of those things which has degree p+1, dimension p+1, sorry, degree p+1. So any one of these quotients will have dimension p+1. In particular, you notice that VR mod VR1 is periodic in R mod P minus 1, right? Because if you take M to be 0, then you just get induction B to gamma D to the R. And D to the R is periodic mod P minus 1 because, you know, D is in a finite field. So if you replace R by some S, then D to the R is congruent to D to the S. They're equal. And that immediately says that VR mod VR1 is also periodic. And remarkably, this was in Glover's original paper, this was proved in some ad hoc way. So he has a fairly long proof, a half a page proof. But if you notice that these things are principal series, the proof is very trivial. So one of the things that Ravi and I started wondering about is there some periodicity for the higher quotients? So VR mod VR1 is periodic. What about VR mod VRM? So we came up with the following periodicity result. I won't read all the quantifiers there, but basically R and S are large and M is small. So if R is going to S mod P times P minus 1 this time, okay, not mod P minus 1, then in fact the periodicity can be, you can have some slightly more general periodicity result. VR mod VRM is isomorphic to VS mod VSM. Okay, so for an M is equal to 1, we already knew this by Glauer. In fact, you don't need R to be congruent to S mod P times P minus 1. You just need R to be congruent to S mod P minus 1. But if you're willing to throw in the P times P minus 1, then you get this. And I leave you to guess what a generalization of this would be for if M becomes bigger and bigger, goes beyond P. There's some very obvious statement here. But this is the one that we needed, and we could prove this. And since every talk's supposed to have a proof, let me give you a quick proof. Quite pleased about this proof because it uses some objects from deformation theory, which is a subject that number theorists study quite a bit. And one of the things that appear in deformation theory is not the field FP, but the ring FP epsilon mod epsilon to the M. Okay, so when M is 2, those are just what are called the dual numbers. Okay, so I'm going to give a proof, a one-line proof using these dual numbers and their higher analogs. So let gamma R be GL2R. So GL2 is some sort of group, but you can plug in fields as Anand Sawan did in the opening talk, finite fields or infinite fields. But you can also plug in rings, right? You still get a group. So gamma R is GL2R for that ring. And BR is similarly the Borel, the upper triangular matrices, but the entries now are in R. Okay, and then we define a map from VR to this sort of generalized principal series, but you know, it's induction from BR to gamma R this time. The same definition, D to the R. And we take the polynomial Pxy to some function. And what function is that going to be? It just takes gamma to P of CD. And then it's a nice, very pleasant check to see that this map is actually FP linear and gamma linear. And so you get a morphism from VR to the right side. And the kernel of this map is exactly VRM. And then as we observed in the case of Glauer, that character D to the R is periodic mod P times P minus 1. If your ring R is in that range, then your character there is periodic mod P times P minus 1. So if R is going to S, mod P times P minus 1, then D to the R is equal to D to the S, and therefore the right-hand side doesn't change. And therefore you can see that VR mod VRM is the same as VR, is periodic. It's the same as VS mod VSM. There's something more one has to check because this map is not actually an isomorphism. It's only surjective if M equals 1. But the point is that the right-hand side, periodicity of the right-hand side forces periodicity of the left-hand side. Okay, so we want to move on now. So we defined, just to recap where we are, we first defined VR, the symmetric power representations of GL2FP. Then we defined some monomial submodules, the XR, XR minus 1, XR minus 2, etc. And we also defined some theta submodules. VR0, VR1, VR2, right? 2 different filtrations. Now we want to combine these and look at quotients which use both of these submodules. So here's the definition. We look at VR and we take the quotient of VR by XR minus I. That's what the I is there in QI. but we also quotient out by VR to the I plus 1. Okay, so it's not so clear why not we take I and J, but these are the ones that are very interesting for us for applications. Okay. So it follows from the previous lemma that because VR mod VRI plus 1 is periodic, that the QIs are in fact periodic in R modulo P times P minus 1. Okay, so this is one observation. So let's do some simple examples. When I is 0, that's the simplest case. Well, VR mod VR1, we just said that many times, it has two journal holder factors, and I is 0, so XR minus I is just XR. It kills one of the journal holder factors, and Q0 is just then one particular journal holder factor, and that's what it is. It's one of the irreducibles, and then that's the formula for what you get. Vp minus 1 minus A tensor dA. Notice that P minus 1 minus A is smaller than P minus 1. You can also compute Q1, and it has 1 to 3 explicit journal holder factors. Again, I won't write them down, but they're basically 3 cases. When you get 1, when you get 2, when you get 3. And so you can work out Q0 and Q1 explicitly. So one of the things that Ravi has done is he has come up with an algorithm to in fact compute Qi, all the journal holder factors for Qi, as I varies between 0 and P minus 1. And this is not easy because XR minus I is slightly erratically behaved. Even though VR mod VRI plus 1 is well behaved, XR minus I is slightly erratically behaved. So there's some cases and some things that have to be done here. And he will hopefully tell you more details about this. Okay, so the theorem is that the quotient Qi has between 1 and 2i plus 1 explicit journal holder factors. The fact that it has that many journal holder factors is not at all hard, but you can explicitly write them down, as I did for Q0. Okay, so much I think for representations of GL2FP gamma. Now we want to move to representations of GL2QP, which are a lot trickier. So just so that I don't have to write GL2QP many, many times, please note that G is again GL2QP. There are many groups in this talk, but G will appear a lot. So it's GL2 of an infinite field, the field of p-adic numbers. Okay, and some more notation. We have, just like QP has its integers, ZP, similarly, G has the subgroup GL2ZP, which we'll denote by K, and this is a compact open subgroup of G. And then you have the diagonal matrices, isomorphic to a copy of QP star, this AA sitting on the diagonal, where A is in QP star, and we'll call that the center, Z. Okay, so I said that the tree will come back into this talk. So notice that GL2QP acts on lattices inside QP squared. So, okay, let's break this down a little bit. So QP plus QP has lattices. Lattice, what do I mean by lattice? Basically, I mean something which is isomorphic to two copies of ZP. So ZP plus ZP sits inside QP plus QP, but in many ways, there are many copies of ZP plus ZP inside QP plus QP. So GL2QP moves these lattices around because if you have two basis vectors, E1 and E2, you can just make them act and you'll get another lattice, right? So what we do is we look at the tree. This tree is a pictorial representation of all the lattices and all the inclusion relations between them. And the center dot there is the standard lattice, let's say generated by 1, 0, and 0, 1, ZP linear combinations of that. And then what we do is so the vertices are all the lattice. The edges are the inclusion relations. So if you've done a little bit of first year algebra, you know that inside Z plus Z, there are 3 lattices of index 2, not just 2Z plus Z and Z plus 2Z, but there's also a diagonal lattice. The sort of all entries inside Z plus Z, which are either both even or both odd, X congruent to Y mod 2. That's another lattice inside Z plus Z. So there are 3 lattices. So those are those 3 dots. I'm doing this for P equals 2. And I was giving an example for Z, but ZP is exactly the same argument. So the central dot is the standard lattice, and then those 3 dots reaching out from it are those 3 lattices I just talked about, and so on and so forth. Okay, so that is the Bruhatitz tree. And though I said that p is greater than or equal to 3 in this talk, it gets trickier and trickier to draw this, and especially find pictures on the internet. So here's the picture for p equals 2, which is complicated enough. So I'll just read what's written at the bottom. The vertices are homothetic classes of lattices, to be a bit more precise. I'll leave that for you to figure out. It's just something easy. And whose edges correspond to inclusion relations among lattices. And that also needs to be made a bit more precise because we replaced lattices by homothetic classes of lattices. So it's multiplying lattices by a scalar. Okay, so this tree in general has valency p plus 1. So this is a very central object, and many of the representations that appear are basically going to be some sort of functions on the tree. Can people hear me? Let me just pause for a second. There's been long silences. Can one of the organizers say everything is okay?
Yeah, everything is clear.
Okay, great. Am I going too slowly?
No, I don't think so.
Okay. Okay, so now we want to move from the tree to representations of G. How do we do this? So you start with a mod P representation of gamma. We've seen many of them, right? So if you have a mod P representation of GL2 FP, then you immediately get a representation of GL2 ZP by surjecting GL2 ZP onto GL2 FP. And then you can make the diagonal matrix P act trivially. So this becomes a representation of KZ. Okay. So starting from a representation of GL2 FP, we got a representation of KZ, but how do we get a representation of G? Well, KZ acts by G on the left, it's a subgroup, and it acts on V, as we just described in the line above. So KZ acts on G cross V, and then you can take the projection to the first factor, KZ to G. And we just said that was the tree, right? Because G acts transitively on the lattices, and KZ was the stabilizer of the standard lattice. So that's just the tree. So we have this kind of collection of vector spaces sitting above the tree. And we will define sections of this cover. So a section has the obvious definition, but I wrote it out here. It's all functions from G to V, such that again, f of hg is h times f of g for all h in kz and g in g. Okay, so this is the condition that the function has to satisfy. So if you have a section, what is a section? Is something from a function from the right to the left. On the first coordinate, it's kind of forced what you have to do, right? Because if you have a little g on the first coordinate, it has to be little g. But on the second coordinate, you have some ambiguity. So you call that f of g. So it's something at v, and that's how you get your function. And then this condition is more or less forced on you. F of hg is h dot f of g to make things well defined. But there's a little more technical condition. We also require that f is compactly supported mod kz. Okay? So what does it mean that f is compactly supported mod kz? First, note that that kz really acts on the support, right? Because of that condition, f of hg is h dot f of g. So it makes sense to speak of support z, kz backslash support of f. And because kz is open, I said k was open, so kz is open in G, the support mod kz has the discrete topology. And because it's compactly supported, this thing is in fact finite, the support. So one could drop that fancy language, f is compactly supported mod kz, to just say f is finitely supported mod kz. Basically, it's on finitely many cosets, it takes some values, and then within the cosets, you can get the values by these translations. All right, and this is a G module via right translation in the usual way, just as we did for the, when we were defining the principal series, which was induction from the Borel. This is induction from KZ, by the way. So a very simple instance of this is if V is the trivial representation, then this in space of sections, well, what is this relation f of hg, h dot f of g? The action of h on f of g is trivial. So it's just f of hg is f of g. So it's just functions on the tree. And these are just finitely supported functions on the tree. So the simplest case of this somewhat general construction is basically the Bruhat-Titz tree along with some numbers on the vertices of this tree between 0 and p minus 1, which are the values of the function at that point. And it's compactly supported. Within a ball, you have some non-zero things, and outside this ball, you don't have anything. So it's a very, very simple kind of object. So all we're looking at are these graphs with numbers on them. Though on this page, you will not be able to tell that to a graph theorist if you just show them this page, right? It's just basically some tree with some numbers on it, and the numbers are compactly supported. And more generally, if you have a coefficient system V, then you get something a bit more complicated. It's not much more difficult from this. Okay, so now here comes an extremely important definition. So remember, in the KZ, G, V are basically functions on the tree. I mean, when V was trivial, they're just those compactly supported functions on the tree. So one very natural operator is the sum of neighbors operator. If you have a function and you want to define a new function, well, how can you do this? Well, at any point on the tree, you can add up the values of all the neighbors of that particular vertex and decree that to be the new value at that point. Okay, the sum of neighbors operator. So this is a very canonical thing to do in graph theory. And if you have a more general coefficient system V, then you get in general a more complicated definition for the Heck operator. And it turns out that this map is certainly G equivariant, right? Because if you add up the values on the tree, you get one thing, but if you shift and add, it's the same thing as adding and then shifting, right? So it doesn't change anything. I mean, adding and shifting and adding are the same thing. So this is a G equivariant map. In fact, this is the only G equivariant map there is. The endomorphism algebra is completely generated by this one canonical operator, the Heck operator. Okay, as I said, in the very silly case of the trivial representation, where you just have these graphs with a bunch of dots on it, a bunch of numbers on it, then the value at any point is just the value of the sum of the neighbors of that point. Okay, now if you think about it a little bit, let's just take lambda to be 0 for a second. The operator T is injective. Because, you know, if you have just like the graph with just one non-zero point, that's going to propagate once you apply T to it, right? You take the sum of neighbors, it's going to give you a whole bunch of non-zero things. Just take the graph where everything is 0 except at the origin you have a 1. If you look at T of that function, well, around that thing, you're going to take sum of neighbors and the 1 will propagate. So non-zero functions sort of blow up, they become non-zero, more than non-zero. So T is injective. And T minus lambda just means you're multiplying a function by lambda. So it's a sum of two operators. That's lambda times identity operator. So that continues to be injective, but it is not surjective. And I'll leave you to think about that for a bit. Okay. So once you have a G equivariant operator, which is injective but not surjective, the kernel is not very interesting because it's injective, but the co-kernels of these operators can be very interesting. And they give new representations. So that is the basis behind this definition. The induction KZGVR is the space of all functions. And then we're modding out by the image of T minus lambda. So that's the co-kernel. Okay, it wasn't surjective, so that's a non-zero space. And then we twist that by some characters, eta composed with det. So if you just look a couple of lines above, R is small, lambda is a non-zero scalar, and eta is a character. And so this is the basic representation, pi r lambda eta, which I will use again and again. Okay, so these mod PG representations are essentially irreducible, which is very surprising. Notice that we just modded out by the image of T minus lambda, but there's no one to say that the co-kernel should be irreducible, but they're essentially irreducible. So that's one fact. And they turn out to be the basic building blocks of the mod P representations of GL2QP. Okay, they'll come up again and again. So I'll make this a bit more precise, I think, in the next slide. Why are they the basic building blocks? You can write all the representations in 4 families, and they're all more or less built out of this pi r lambda eta. So I think here they are. Before I do that, I'm going really slowly. So let me tell you about one of the 3 classes of representations. So for example, if you take the trivial representation, then there's something very combinatorial you can do. Remember, the trivial representation is just compactly supported functions on the tree, right? Just basically those graphs, which are a bunch of non-zero values. And you can look at the total sum of any particular function because it's compactly supported. You just add up all the values and you get a number, right? Okay, so that's a very canonical thing to do. And clearly, the total sum of TF was the sum of neighbors of everything, right? Is P plus 1 times the total sum of F, because you've overcounted P plus 1 times, right? Each vertex has P plus 1 neighbors. So if you first do that, and then you then take total sum, you'll get P plus 1 times the total sum. But P is 0. So when you push everything into FP bar, then TF and F have the same total sum. That P plus 1 times the total sum just becomes 1 times the total sum. So TF minus F goes to 0. And another way to say that is that that map factors through T minus 1. And now that's beginning to look very much like one of the representations on the previous slide. It's beginning to look like pi 0, 1. The last one there is the identity character. I didn't twist by anything. So R was 0, so that's the pi 0, and then we're modding out by T minus 1. So we get a factorization through through 1, and so pi 0, 1, 1 is no longer, unfortunately, irreducible because it had a FP bar as a quotient, but the kernel now turns out to be irreducible, and it's called the Steinberg representation. Okay, so this is how you can build some of the representations out of these pi r lambda etas. Okay, so I will now tell you the classification. Before I do that, let me just say that there are some topologies involved, and we always want to work in the category of smooth representation. So a mod P representation of GL2QP is said to be smooth if the stabilizers of vectors are open. Okay, this is what will guarantee that the natural action of G on the vector space of pi to pi, this action is continuous. Okay, so this word is always there in the background. Okay, so here is the classification. Eta will denote a character. It's a theorem of the following people: Barthel Livna in 2 papers, and Duke and JNT, 1904 and 95, and then Breuil and Compositio and Jussieu actually has 2 papers as well, but they were both in the same year. They say, these authors say, that there are 4 classes of smooth irreducible mod P representations of G. Okay, so they're the one-dimensional ones. You know, there's a silly representation of GL2QP. You just take the determinant, then you get something in QP star, and then you take a character, and eta, you just apply eta to it, you get something in FP bar star. So those one-dimensional representations, eta composed with eta, are always there. But more interestingly, you have the Steinbergs and twists of them. We just did that one. You have what are called the principal series representations for GL2QP, but here it's pi r lambda eta, but the r's are small, but the lambdas have some condition on them. They're not allowed to be plus minus 1 if r is 0 or p minus 1. We just saw when r was 0 and a lambda was 1, then that pi 1 0, pi 0 1 1 was not irreducible. So you need to drop some values, some finitely many values of everything's finite anyway, but some values of r and lambda to make that irreducible. And it's not clear why these are called principal series, because this is compact induction, right? But I'll explain that in a second. And finally, by the way, in case 3, I should have said the lambdas are non-zero. And finally, you have the representations with lambda equal to 0. And these turn out to what are called supercuspidals. Okay, so this is a complete list of all the representations of GL2QP acting on smooth representations, acting on mod P vector spaces, this FP bar stuff. And I wanted to say why in case 3 it's called a principal series. It turns out that the compact induction in case 3 is also a Borel induction. And there's a formula there, and the notation for that formula is going to come up in later slides, but I thought I'd just write it. So there's an isomorphism of some kind. Okay. So this is the classification of Barthel, Livna, and Breuil. Barthel, Livna actually did the first 3 cases, and Breuil showed that in fact the remaining representations were in case 4, and that they were irreducible in fact. And there was a complete list of things which are not in case 1, 2, and 3 were the ones in case 4. Very simple representations. Okay, so one more word I want to use, and that is the word admissible. So a smooth representation, mod P representation always, is admissible if the invariant vectors under a compact, every compact open subgroup of G are finite dimensional. So pi to the k, that's the usual notation of invariant vectors, where k is a compact open, that space is finite dimensional. Okay, so this is a condition that is very classical. It appears in all the automorphic forms language. It goes back maybe to Harish Chandra, who studied this for GK modules, etc. But it's everywhere in the literature. And one can ask whether this property also holds in the mod P setting. Okay, so it turns out that in fact, each of the 4 families of representations in the Barthel-Livner-Breuil classification is in fact admissible. The K invariant vectors are always finite dimensional, and K is a compact open. Okay, and this is a check. You physically just mentally, I mean not mentally, physically check this. You don't have to do a computation. Okay, there's no theoretical reason why this should be true. It just happens to be true. Let me make a remark. As soon as you have an admissible representation, then it automatically has a central character. The center Z has to act by a scalar. Okay, and so this is a nice a remark, a proof of which was explained to me by Sandeep Verma a few days ago. It's very trivial, it's in all books, but I'd forgotten. And what is the proof? The proof is that if you have a compact open and you look at pi to the k, then it's finite dimensional, and any scalar will preserve this space. Okay, so you have now a scalar acting on a finite dimensional space, and everything's algebraically closed, so you'll have an eigenvalue, and you'll have a non-zero eigenvector. And now if you look at the eigenspace, well, that's G stable because Z was central. And if it's G stable by reducibility, it forces it to blow up and be the whole thing. So basically, Z doesn't just act on those vectors by lambda, but it acts on the whole thing by lambda. So that's why every admissible representation has a central character. Okay, so this is a standard fact in the subject. The classification was originally done for smooth. There's some nice comments I want to make. The classification of Breuil, etc., was done for smooth, initially done for smooth irreducible representation with central character, though I didn't write it there. And the reason is that later Berger showed that in fact every smooth irreducible mod P rep has a central character. So if you put all the facts together on this slide, you obtain the following theorem, which is a mix of some serendipity and various other things. Every smooth irreducible mod P representation of G is admissible. Okay, it's because A, you can classify the ones with central character and they all turn out to be admissible by a physical check. And then some other ad hoc argument shows that in fact, every smooth irreducible does have a central character. And so you get this result. And this is a reflection of a theorem which is sort of well known when you work over the complex numbers, GL2QP, and you're working over the complex numbers. It's a fact going back to Jacquet-Ohl theorem, I think 70s, 80s, I can't remember. So every smooth irreducible representation of GL2QP of the complex numbers is admissible. And we are seeing a mirror of this fact in the mod P world. So you may ask whether such a theorem is true in general. For example, if you replace, I'm going to do a little bit of an aside because it's quite interesting. So just for 2 slides, I'm going to ask whether this theorem is true for GL2 of a finite extension of QP, even though I haven't defined what they are in this talk. But just bear with me. So the question is every smooth irreducible mod P rep always admissible? So remarkably, it was shown by Daniel Lee that this is false when QP is replaced by a more general p-adic field. In particular, he looked at the following p-adic fields. He looked at the degree F extension of QP. Okay, so QPF is what is called the unique unramified extension of QP. Okay, so this is a generalization of the p-adic numbers, and I won't define it here, but trust me that there's one for every F. In fact, what he did was he showed that there's a non-admissible smooth irreducible mod P rep for GL2 QPF for each F greater than 1. But in fact, he did this for F greater than 3. Okay, of course, for F equals 1, we just said it's not, everything is admissible. But for F greater than or equal to 3, he used these diagrams of Breuil and Pascunas. I'm just going to throw a few words around here. As I said, these slides are just a bit of extra information. He used what are called these diagrams of Breuil and Pascunas to construct these non-admissible irreducibles. It's a very clever argument, a very short paper in Math Research Letters, and appeared last year. So Bro and Pascunas looked at what are called finite dimensional diagrams, and this is an infinite sum of these diagrams. And then he put some slightly strange action of GL2QP on this diagram and managed to construct these representations, which are non-admissible. His argument doesn't work for f equals 2. So about a year ago, I asked Mihir Sheth about this, and he came up with a very clever way to get around this. So these diagrams that Lee looked at were attached to irreducible two-dimensional mod p-Gal representations, and Sheth decided to look at a reducible split mod p-Gal representation. And using this particular diagram, you can in fact give a simpler construction of a non-admissible irreducible mod p rep. So it's very, very heavily false that for more general p-adic fields, GL2QP has GL2F, capital F has the property that all smooth irreducibles are admissible. Okay, so there were a bit of stuff on Gal representation, so that is a good segue into talking about Gal representations, because these diagrams, it's kind of ironic. You want to study these mod p representations purely on the so-called automorphic side. You want to study these mod p representations of G, GL2QP or GL2QPF, but you have to use Gal representations as a crutch in between to study them. And so that leads nicely into Galois representations. Let me talk about Galois representations now. So I'm going to concentrate on mod p Galois representations, but there will be some characteristic zero Galois representations also floating around towards the end. So for notation, remember QPF was the finite extension, finite degree extension of QP of degree F, and we let its Galois group be GQPF. So these are all automorphisms of QP bar fixing QPF. I need some characters of these Galois groups. So these are what are called the fundamental characters of level F. They're very canonically defined. Notice that there's a lot of notation in subscripts and superscripts and things, but it's quite simple. On the left-hand side, you have a Galois group, and on the right-hand side, you have a finite field, but not with P elements anymore. It has Q elements, where Q is P to the F, and non-zero elements. It's a homomorphism. So today morning, Mahesh said he will not define what omega is. So let me do that for you. Omega is the first fundamental character of level 1. And in general, the fundamental characters of any level F are defined by what is called Kummer theory. You just take a root of minus p, in particular p to the fth minus 1th root of minus p, and if you make sigma act on it, you get the original object up to p to the f minus 1th root of unity, right? Omega f of sigma is a p to the f minus 1th root of unity. So that is it. That defines what omega f of sigma is for every sigma in the Galois group. It's a root of unity, but the roots of unity are exactly in that are canonically isomorphic to FPF star. Okay, so you get a character into FPF star. So in this talk, I'm only going to use omega 1 and omega 2 because everything is two-dimensional. But if you were working with GL3 or GL4, you'd need fundamental characters of higher levels. There's one more character that came up a few slides ago, and I said it'll come up later. So eta lambda is another character of GQP. It takes geometric Frobenius. So that's more or less the canonical generator. Frobenius P is the generator of the Galois group of QP modulo the inertia group. We take the inverse of that and we send it to lambda. Okay, so unramified means that on inertia it's trivial. So these are the two basic kind of characters that will show up. The omega f's are ramified characters. They're tamely ramified characters, and their eta lambdas are unramified characters. So ramified and unramified. And every two-dimensional semi-simple mod p representation of Galois group of QP can be built out of these things. And here is let me write both of them at the same time. Okay, let me do one at a time. So the reducible ones are just direct sums. So you have two powers of fundamental characters of level 1. And in front, you have some unramified characters, eta lambda and eta mu. And then you have also yet another induction, but this is Galois induction from the index 2 subgroup of the Galois group of QP, the Galois group of QP squared, of omega 2 to the c. C is just an integer. Omega 2 is the fundamental character of level 2. You take a power, it's a character of GQP squared, you induce it. So you get a two-dimensional representation, and you can twist it with eta lambda or eta gamma, where gamma is a non-zero element in FP bar star. You can twist these things, and so this is a whole family of two-dimensional representations. So both are two-dimensional, 1 + 1 or 2. Okay, it said my internet connection is unstable. Can you hear me, Amri?
Yeah, you're clear.
Okay, great. It briefly flashed on my screen. Okay, so this is a complete list of all two-dimensional representations of the Galois group of QP. And I would like to connect these now to the representations we were talking about earlier. So here is a remarkable map. You know, these Langlands correspondences sound very abstract, but you know, here we're doing everything about P. It's basically some sort of computer science, not really mathematics. Everything is more or less finite and countable, and things like count things and make lists and things. So here's this map from the mod P representations of the Galois group of QP to mod P representations of GL2QP, which I was calling G. So this is called the local Langlands correspondence, mod P local Langlands correspondence. And remember, on the left-hand side, there were two families of Galois representations, the reducible ones and the irreducible ones. So on the reducible ones, there's a direct sum in there. If you can see it, there's a direct sum there. It goes to a sum of those two of the pi r lambda etas, if lambda is not equal to 0. So eta lambda was that unramified character. It was only defined if lambda was not equal to 0. So this is what, you don't have to understand everything here. I'm just trying to give a rough flavor of it. That if you have a direct sum of two characters on the left, you get a direct sum of two basically principal series representations on the right. Unfortunately, they're not always irreducible because lambda could be 1 or something, and then you have to do something else. You have to take the semi-simplification. R prime, it will be defined at the bottom. It's basically P minus 3 minus R. So it's just some flip of R. Okay? So lambda, and then there's lambda inverse and eta, and there's that. And then there's this two-dimensional induced representation, and that goes to a supercuspidal, pi r0 eta, if lambda is equal to 0. Okay, so this is the mod P Langlands correspondence. And as I said, I'll define R prime. R prime is the unique number congruent to P minus 3 minus R in that set, 0 to P minus 2, mod P minus 1. So it's just a kind of a shift. Later, right on the last slide, I will use the fact that when R is P minus 2, R prime is just R, right? If you put in P minus 3 minus P minus 2, you'll get minus 1. So you have to add P minus 1 to that, and you get P minus 2. So R prime is minus 1 is not in the set, so you have to replace it by P minus 2. Okay, so I'll use that on the last slide. So just remember that reducibles go to sums of principal series, and these induced representations, these dihedral representations, two-dimensional dihedrals on the left go to supercuspidal. Everything on the right is infinite dimensional, everything on the left is two-dimensional. Okay, so that's the mod P local Langlands correspondence. Okay, so now let me tell you why I introduced that. So there's a very classical problem in number theory, and that is to study characteristic zero Galois representations and their reductions. So there are certain irreducible two-dimensional representations, VKAP, of the Galois group of QP, which are defined not over QP, but finite extensions of QP. It's not important what those finite extensions are. They're parameterized by integers k greater than or equal to 2. Those are called the Hochstate weights and things, but it's not important here. And certain elements AP, which I said they were defined over finite extensions of QP. QP bar is the algebraic closure. And V is called the slope of these things. And I'm requiring that p-adic valuation of AP, which is V, I'm requiring that to be positive. Okay, so these parameterize basically all irreducible two-dimensional representations of the Galois group of QP. Okay, so you have a representation from GL2 QP, G Galois group of QP to GL2 of a p-adic field. And one thing you can do is you can take a lattice in here and go mod P, and you get its reduction. So you get a mod P representation of the Galois group of QP, and you can ask what it is. Is it of type 1 or of type 2? Is it reducible or is it irreducible? And that question is an extremely hard classical question. And the techniques that one has introduced so far can be used to actually answer that question in some cases. Let me just say that if this looks very abstract for people working in modular forms, the VKAPs are basically the local Galois representations attached to modular forms. Okay, that's what that says there. So they're not something too mysterious. Where P is prime to the level. And K is the weight of the form, etc. Obvious notation, AP is the p-th coefficient of the form. Okay, but I haven't defined the representation precisely, just by some notation. So as I was saying, if you have a representation to GL2 of a finite extension of QP, you can conjugate it to lie in GL2 of a finite extension of ZP. And then you can go modular maximal ideal, and you get something in GL2 of FP bar, finite extension of FP, so in GL2 FP bar. So this is called the reduction, and it's only well defined up to semi-simplification because it depends on a choice of lattice, but up to how you conjugate, etc. But we will always look at the semi-simplification of this. The reducibility or the irreducibility of that doesn't change, right, up to semi-simplification. So here's that classical question. This goes back to Fontaine, etc. What is the reduction of these crystalline representations as a semi-simple two-dimensional Markov representation of the Galois group of QP? So Fontaine himself answered this for small weights when k is less than p minus 1. And Broglie invented the p-adic, the Markov local Langlands correspondence to extend his results up to weight 2p minus 1 or something like that. So for small weights, this is known by their work, and it's also known for large slopes, where the p-adic valuation of AP is very large. But it's open in general, and in particular, it's not known for small slopes. So as an application of everything in this talk so far, and in particular of the Markov local Langlands correspondence, there is the following theorem. Let p be bigger than or equal to 5, then one can write down the reduction explicitly for all small slopes. Remember, v was positive. This industry was started off by Buzzard G in 2 papers up to slope 1, though they couldn't do slope half initially, and then they cleaned it up later. And then we started looking at things between slope 1 and 2, and Shanli Bhattacharya could do all slopes between 1 and 2 except 3 halves. Meanwhile, the missing case of slope 1 was done also with Rosenstein, Sandra Rosenstein and Ian S. Leon. And finally, this missing case of slope 1.5 was done recently by Vivek Rai, who was a postdoc now at ICER. This is still a preprint. Okay, so how is the Markov LLC used exactly to answer this question? Let us take a look at that. So before I do that, I'll just make some remarks about, I didn't really tell you what the answers are for the reduction, whether you get something reducible or what. So I'll just make some qualitative remarks that you mostly get something reducible when your slope is integral, like slope 1, but it's mostly irreducible if your slope is between 0 and 1 or between 1 and 2 strictly. If it's fractional slopes, you tend to get irreducible things. And I won't tell you all the characters that you actually get. The behavior at these special slopes, half, 1, 3 halves, these half integral slopes is very tricky. And in particular, when the weights satisfy some congruence condition, these are called the exceptional weights, when k is congruent to 2v plus 2, mod p minus 1, all kinds of hell breaks loose. But now at least there's a conjecture which says what should happen. And it says that there's an alternating sequence of irreducible and reducible possibilities that should occur. And I'll just leave it as a qualitative statement like that for now. But I'll come back to this at the end of the talk. Okay, so this is a conjecture in general. It's been solved now for 1.5 by Vivek Rai. And finally, I should also say that when one writes things down, one notices some patterns between slope v plus 1 and slope v. And there is a general principle that explains this, which uses Hida families and the theta operator. But this is a talk in its own right. And there, I won't say more about this. This is a preprint with Arvind Kumar. Okay, so let me come quickly in 2 slides. Let me tell you how the proof goes. So there's also a p-adic local Langlands correspondence. Okay, so this is also due to Bro and Berger, etc. But there's a functorial version due to Colmaze in 2010, which associates to VKAP the G representation pi k AP, which is given by a very similar formula, compact induction, and then modulo T minus AP. But this time it's characteristic 0. There's a QP bar squared there. Okay, so you can guess what the definition is because everything has more or less been defined many times now, but it's a little bit slightly different context. It's a characteristic 0 thing. And the point is that the p-adic local Langlands correspondence is a characteristic 0 matching up of representations. It commutes with the Botp local Langlands correspondence. with respect to the process of reduction. So let me explain that. So we have these crystalline representations, characteristic 01s, VKAPs on Galois representations. And the p-adic local Langlands correspondence associates these automorphic representations, automorphic size, everything is local here, so, but representations of GL2QP, these pi KAPs, right? That's the p-adic local Langlands correspondence. And we're interested in studying the reduction on the left. But you could also look at the reduction on the right, which is now a mod P representation of either the Galois group of QP or of G, GL2QP. And as I was saying, the mod P local Langlands correspondence, which is an arrow on the bottom, it makes this square commute. This is really remarkable. So that very ad hoc definition of the mod P local Langlands correspondence that we saw earlier, given by Broy, is canonical in the sense that it makes this diagram commute. It doesn't matter whether you go over on the top, look at the pi KAP and take its reduction, or you go downwards, take the reduction and apply local Langlands, mod P local Langlands, you'll get the same representation. Okay, so this is the basic idea. So if you want to compute the reduction on the left, you may as well compute the reduction on the right. And to do that, everything that I've said in this talk is used, and I will explain that in one slide. So it suffices to compute the reduction on the right, pi bar SSKAP of pi KAP. I should say that this map here, the mod P local Langlands correspondence is injective. So once you know what's happening in the bottom right corner here, you can invert the mod P local Langlands correspondence and come up with what's happening in the bottom left. Okay, so we just have to work on the right-hand side of this square. This suffices to compute the reduction. And for that, we need to have a lattice inside this huge infinite space. And we take the standard lattice, which is the image of these kinds of functions, sim k minus 2 zp bar squared. These are functions from G to sim to polynomial representations, but the coefficients now are over zp bar, which is the integers in qp bar. Okay, so we look at the image of this thing in pi KAP. And of course, if you reduce this, then you just get the reduction by definition. So notice that there's a natural surjection between int k z g vr and theta bar KAP. So there's a natural surjection like this. And the reason is that if you look at the third line on this slide, theta KAP, then you have this image of this sim k minus 2 zp bar square stuff sitting in there. But if you go mod P, then it'll factor through sim k minus 2 fp bar squared. And remember, that was just VR. The second last line of this slide says that VR is just sim r fp bar squared, where r is k minus 2. So it factors through this thing. So all of a sudden, if you're trying to understand the reductions of crystalline representations, you need to understand the Jordan-Holder factors and the various submodules of VR, which is how I started off this lecture. Okay, so this slide finishes the proof. It turns out that if the slope is fractional, then the above map, this map here, the third last line, it further factors through this quotient Qi. Qi, remember, was VR mod VR to the I plus 1. And then you also mod out by XR minus I. But as we mentioned at the beginning, a complete list of Jordan-Holder factors of Qi is not now known for all small values of I. So you have a lot of information now on the left, and this allows you to more or less compute what you have on the right. If you can eliminate some of the Jordan-Holder factors on the left, and this is a very delicate computation with the Heck operator T, if you can cut it down to 1 or 2 Jordan-Holder factors, you pretty much get an isomorphism between the left and the right, and therefore you completely know what theta bar is, and therefore you completely know what pi bar is, and therefore you completely know what V bar is, VKAP bar. Okay, so that's how this works. And as I said, this allows you to compute what VKAP bar is. Similar argument applies if V is integral. This time you don't factor through Qi, you factor through another quotient, which I haven't introduced in this talk, but it's a variant of Qi. Okay, so all well and good, but here's a very important point. Eliminating Jordan-Holder factors on the left is extremely tricky. And that is where the small slope condition is used. it can only be done for small I, or equivalently for small slopes V, because V lies in I to I plus 1. So when I is small, you can eliminate Jordan-Holder factors, and therefore V is forced to be small. That's why we had those small slopes at the beginning, up to slope 2, basically. To show you how tricky this can be, and I'll end in 2 minutes. I'm at the 75-minute mark, which is what I was told to do. There is no way to say which Jordan-Holder factors Ji survive. In fact, I'll just end with this picture. For half integral slopes, V equals I plus a half, each of the 2I plus 1 Jordan-Holder factors Ji seem to occur, 1 or 2 at a time, in the following zigzag pattern. So remember, Qi was basically VR mod VR I plus 1, right? I plus 1 means I plus 1 copies of the theta polynomial in there. And so we break it up into pieces. And each of those pieces has 2 Jordan-Holder factors, J0, J1, and then J1, J2, J2, J3, which are quotients of VR1 and VR2, etc. So what is happening is that when you try and eliminate Jordan-Holder factors, it seems that you first get, J0 never appears, but you first get J1, and then after a while you get J1 and J2 both together. Okay, so remember, when you have 2 Jordan-Holder factors together, it's a direct sum of principal series. So you probably get a reducible Galois representation. Then for a while you only get J2, and then for a while you only get J3. So you get these supercuspitals, and therefore you get irreducible Galois representations. But then suddenly you start getting J3 and J4 together. And again, you get something reducible. And then so on and so forth. You get irreducibles, because first only J4 appears and J5 appears, but then they appear in pairs. So it's an alternate sequence of single Jordan-Holder factors or pairs of Jordan-Holder factors that appear. And they appear in this zigzag pattern. And then right at the end, this J2I plus 1, which is the last Jordan-Holder factor, it turns out that the R here is P minus 2. So the R prime is also P minus 2, by the remark I made some slides ago. And you have some sort of self, the D is for duality. You basically have pi P minus 2 and pi P minus 2 here. And you get another reducible of a very special kind. Okay, so this is how it looks like God wants us to choose the Jordan-Holder factors. And this is how it has played out in real life up till slope 1.5. And the way the Jordan-Holder factors here are selected depend on the size of an explicit parameter tau. So as that parameter gets larger and larger, you start getting this zigzag pattern. As you vary through the whole range of the parameter, you get all the Jordan-Holder factors here in this order. So it's extremely tricky. It's not like there's one canonical Jordan-Holder factor that survives and you can immediately compute theta bar. All of them play a role in some special cases. Okay, so I will end with that. And here are some references in case you're interested. And so thank you very much.
Thank you, Professor Ghate. That was, I wonder if there are any questions from the audience at this point. So I guess you can type your questions into the chat.
Yeah, there is one question in the chat.
Okay, so I don't have it because I got disconnected in the middle and then the chat got cleared. So maybe, can you send it again or maybe just read it out? Okay, so a question on YouTube. What about mod P representations of K, where K is a finite, totally ramified extension of QP?
Yeah, so I didn't talk about those in this talk. You can actually, so Breuer and Pascunas have written a book where they actually construct representations of GL2 QPF, where QPF is a finite unramified extension of QP. But they also have some theorems which, they have many theorems about that, but they also have some, at the beginning of the book, they also construct representations for GL2K, where K is an arbitrary extension of QP. So they have these combinatorial objects called diagrams. Diagram is basically a K representation and then the normalizer of an Oberhori representation, and they're glued together in some way. So they have these diagrams, and they say that basically once you have a diagram, you get a representation which comes from this diagram. I'll be a little vague here. So those kinds of theorems actually work when you have an arbitrary finite extension of QP. But they say a lot more. And for that, they need, for example, for the irreducibility of those representations they construct, they need that K over QP is unramified. And I think, so Michael Shine in Israel have some criteria in how to show these things are irreducible when K is totally ramified over QP, but it's not always, I think, easy to carry that out.
Okay, it seems like there are no more questions in the chat, but I had a question, especially in the finite field case. Do you think it's too early to ask about GL3? Have
yeah,
tried to look at the...
GL3. I think people have started constructing. Some kinds of the p-adic local Langlands correspondences. These kinds of things have started to be done, and people have also people have started work on GL3. It's not like people have not done anything. There are things on GL3.
I was thinking
but there are no
finite fields,
Yeah.
Even
There's no mod p local Langlands correspondence, unfortunately, for GL3. Three-dimensional representations corresponding to these things. That is not known yet, I don't think. And so that is one issue if one wants to carry this out. But in individual corners of the squares, people have been working, individual corners of that square. Just relating things together has not been done.
I was thinking specifically about, at the beginning of your talk, you talked about mod P representations of GL2FP. And so I was wondering about just that part of it. That may be some...
Mod P representations of GL3FP. Yeah, the things must be known. Of course, things must be known. You're an expert on this more than me. Green's theorems,
well, not
GL and FP and things over the complex numbers. Yeah.
Yeah, so, and of course, everything's been known for more than 100 years now.
Yeah. I'll have to think a little bit about what the general statements are for GL and FP mod P, whether everything is completely known. I'd be surprised if it is, but I may be wrong.
Okay, let's see. So audience can unmute and ask questions at this point if they like.
I think GL2 finite extension of FP is classified, right? Instead of GL3 FP, if we extend the finite field, and then the similar result works, just like symmetric powers, but with proper tensor.
Yeah, if you have GL2 of FQ, then you can embed, so you can take various symmetric powers, but you can change the action of GL2 FQ each time by applying Frobenius, powers of Frobenius. So you get many, many different copies of symmetric powers, and the tensor product of all those, and then twisting with characters gives you a complete list of the irreducibles. These kinds of theorems go back to Brouwer and Nesbitt from the 50s, 60s, etc., or maybe even earlier, I'm not sure. But this is a complete list of irreducible representations. So there's Q times Q minus 1 irreducibles for GL2 FQ, if you're working mod P.
Okay, are there any more questions? Well, it seems that there are no more questions. So in that case, let us thank Professor Ghate for this wonderful talk. You can unmute your mics and clap, or you can use the virtual clapping feature of Zoom to do that.
Thank you. Thank you very much.
Thank you.